Okay, so hello everybody, I'm Guillaume Selosia, a third year PhD student, and today I will present a joint work with Mathieu Quinche, my advisor, that is entitled Discontinued Privacy, Personal Data Leaks in Apple Bluetooth Low Energy Protocol. And as part of Apple Continuity Services, we found that messages emitted by BLE devices are leaking private information. So at first, what is Apple Continuity? Apple Continuity gathers popular features such as the well-known airdrop, the instant hotspot, and the on-off one, for instance. And actually, most Apple users are familiar with. And to enable those features, the communication are based on dedicated protocol designed by Apple. So to carry the information between nearby devices, the Apple Continuity Services rely on the Bluetooth Low Energy, also named BLE, technology. And for instance, the Apple on-off protocol enables the transfer of activities between two devices. So as an example, you can start the reading of a web page on one device, such as your iPhone smartphone, and then you can switch to another nearby device, such as your iPad tablet, and pick up where you left off finally. For this transfer to work, the BLE messages must be exchanged between devices. So to carry data, the Apple Continuity Services use the BLE advertisement packet that is represented here. And such packets are broadcasted periodically, so several times per minute. And the data are included in the manufacturer-specific data field that can contain several continuity messages that are all formatted as a type, length, and data. And now, if we look back at previous work on continuity, we can see that some Apple Continuity BLE privacy issues have already been noticed, and especially the work from Becker et al., the one from Martin et al., and our Mobiquitous paper, identified that the BLE continuity messages include the static identifier and non-reset counter that can be used for tracking. And we point out that those issues are related to the content of BLE continuity messages, and that the limitation of those work is that they rely on a partial understanding of the messages. Finally, they only identify the tip of the iceberg. Actually, we identify the rest of the iceberg. So our problem falls into the following. The format of meaning of continuity messages are not public. So to understand the content of such messages, we had recourse to a reverse engineering approach. For this reverse engineering, we relied on some Apple debugging tools, such as Packet Logger and Packet Decoder, which are two tools used by developers. We also generated some custom continuity messages using an open source software on the Bluetooth dongle. And we had recourse to the disassembly of Apple binaries, such as core speech and sharing D. And basically, sharing D is a daemon in charge of continuity functionalities. The result of our study is that we fully reverse engineer the Apple continuity messages. So from now, we thus know the structure of the messages, the purpose of each field, but also the meaning of their values. And as such, we are now able to fully understand the continuity BLE messages. So now we have all the elements and we are ready to find some serious leak. So in the following, we will deal with 4 privacy leaks. The first is the physical tracking that we illustrate through passive and active attacks. The second is a privacy threat where we can spy on a smart home activity. The third is how to recover emails and phone numbers. And the fourth is how to recover Siri voice command spoken by a remote user. So at first, let's introduce a little bit of background about physical tracking. And most physical tracking systems nowadays leverage wireless signals emitted by devices carried by the user over time. And in particular, they leverage an identifier that can be static and that is called a device address. And this identifier is included in all BLE packets. So to prevent the tracking, the device address randomization feature has been introduced in the Bluetooth core specification since version 4.0. So since 2010, And its purpose is to change the real device address periodically for a random value. Um, Actually, in our study, we found that Apple adopted the randomization within its BLE device. So let's move to the physical tracking passive attack. And during our study, we found that continuity messages can embed elements that can be used to track a user. And in particular, the AirPod earphones messages include the battery levels and the lead open counter that can be used for this tracking purpose. So here are the results of our experiment. The vertical bars here symbolize the use of different device addresses. And in the bottom of this chart, we have an indicator that the earphones are in use or are not in use. And if we focus on the lead open counter, that is a counter that is incremented each time the lead is opened, we can see that the value of this counter lasts longer than the lifetime of a device address, and that this counter is not reset between two usage sessions. So as such, it suggests that this artifact can be used as well as the battery levels by a passive attacker to link two consecutive addresses. This attacker can thus defeat the purpose of the address randomization. From now, let's move to the physical tracking active attack. And as a reminder, the handoff protocol allows activities to be transferred between devices associated with the same iCloud account. And the handoff messages are transmitted each time the user interacts, so meaning it opens or runs or closes an handoff enable applications such as Mail, Safari, Maps, Contacts, etc. And those messages are represented here and are composed of an initialization vector that is 2 bytes long, along with an authentication tag and an encrypted payload. Actually, when we send an incorrect initialization vector, such as here, this triggers a connection request. And this request can be captured by a nearby attacker and can be further used to track a device over time and link device associated with the same iCloud account. In principle, our handoff attack is similar to the instant hotspot one that have been introduced by Martin et al. But because our attack relies on handoff messages rather than instant hotspot one, it is far easier to exploit. First, the handoff messages are emitted whenever the user interacts with one of the several compatible applications, whereas the instant hotspot one are only sent when a device searches for Wi-Fi connectivity. And the second reason is that the handoff messages affect a much wider range of device than the instant hotspot one. So now let's move to the smart home activity. And during the study, we found that Apple designed its own connected home framework that is named HomeKit. And all the HomeKit connected devices expose a global state number that is here and that is 2 bytes long. Actually, this state number is incremented when the state of device changes. So when you turn on or off your light bulb, this state number will be incremented. So beyond this global state number, we emit the possibility of spying on the smart home through the BLE messages. And for this study, we used a motion sensor that is here and a connected light bulb that is here. And we collect all the BLE messages emitted by those two appliances, leveraging this Bluetooth dongle that is here and that acts as the Bluetooth sniffer. And then we leverage the global state number to infer the activity in the office. So here are the results of our experiment. And what we can see that the spikes are changes from the global state numbers. So all those spikes. This experiment lasts 2 days, 2 consecutive days. And basically, the blue spikes represent the change in the motion sensor. So when it detects a person, for instance. And the purple spikes, like here and here, represent the change of a light bulb, so when it is turned on or off. And from the observation of those results, we can attest that the passive remote attacker can know when there is activity in the room or when the room is occupied. So now let's move to a serious privacy leaks. So the airdrop protocol that allows file transfer, and the nearby action protocol that is used for Wi-Fi credential sharing, exchange hashed emails and phone number. And basically, the emails and phone number are used for friendly device identification. So those identifiers are more likely to recognize people who know each other because they are present in their contact list. So typically, there is a lookup in the contact list, and the match indicates that people know each other. Actually, we found that the clear text values of the emails and phone numbers can be easily reversed via a guesswork attack. And we point out that a guesswork attack is a brute force attack for re-identification. So to evaluate such an attack, we evaluate an hypothetical guesswork attack. So the presented result here correspond to an estimation of performance. And for this attack, we leverage multiple sets of phone numbers and emails. And we also leverage two metrics. The first is the guesswork time, and the second is the average number of matching identifier. And we also point out that a hash can match multiple identifiers. So for instance, when a hash is 16 bytes long, such as hash emitted by airdrop protocol, we can have the ambiguity in the result. Also, another observation that we can depict in this table is that the worst case, so all the existing email address can be tested within 1 hour. So it means that our attack is practical because the computation time is not really an issue. What we can also observe is that when the set is crowded with several thousand entries, the identifier can be recovered without ambiguity, and it's just a matter of seconds. So now let's move to Siri. So Siri is a virtual voice assistant of Apple, like Alexa for Google. And basically, all the Siri messages include the perceptual hash that is of the voice command that is here, and that is 2 bytes long. And this perceptual hash is transmitted at each voice command. Actually, the perceptual hash function works as the following. So it takes as an input an audio signal, and it outputs a hash. And basically, a small variation in the entry implies a small variation in the hash or not. So a small variation in the audio signal will imply a small variation in the hash. So that's why the perceptual hash function is really different from the cryptographic hash function. So beyond the perceptual hash, we emit the possibility that the spoken commands could be recovered via a dictionary attack. And to evaluate the feasibility of this attack, we divided our attack into two phases. The first is that we constituted a dictionary of hashes associated with a set of 100 representative commands that are here. And then we replace this set of commands with 50% in the dictionary and 50% outside the dictionary. And we read the commands one by one to the iPhone and record the corresponding BLE messages. Then for each element of the second phase, we associated the closest element of the first phase. And to avoid the inconsistent matches, we discard matches that have a distance larger than the threshold epsilon. So here are the results of this experiment. And we have first a first parameter that is epsilon, and that is a threshold for the Hamming distance between the matched hash. And we also point out that the hash are considered as binary values, so sequence of bits. We also measured how successful the attack was by its precision on recall. And basically, the precision is the proportion of correctly matched command among all match command. And the recall is the proportion of correctly matched command. So if we take a look at this point where epsilon equals 0, meaning that we have a correctly identified the command leveraging the perceptual hash. We can assess that we obtain a precision of 67% with a recall of 52%. And we also highlight that those results are to be taken carefully because they are likely to be overestimated, and when the size of the dictionary will increase, the precision will diminish. So in conclusion, we expose a wide range of privacy issues. So at first, we leverage a comprehensive reverse engineering, and then we expose how elements included in the continuity messages can be used for passive and active tracking attack. So for instance, battery level and lead open count in the AirPods earphone, but also how to actively track a device based on the replay attack of the corrupted handoff messages. We also expose how to spy on a smart home activity through the global state number that is included in HomeKit messages. We show how to recover the emails and phone numbers that are emitted by the airdrop on nearby action protocol. We also show how to recover the spoken command from the observation of the Siri perceptual hashes. And in our paper, we also discuss some other issues. Actually, it affects all the Apple and partner company devices. So more than 1.5 billion devices that are used by hundreds of million users. And our study also demonstrates that the security by obscurity does not work once again. And actually, if you are interested in studying those messages, we released a Wireshark dissector that you can find on our GitHub. As a second conclusion, we notified Apple of the privacy vulnerabilities in May 2019, and they acknowledged the notification, but we renewed the experiment, and as of today, most attacks are still valid, even if we made some recommendation that could be used to reduce those attacks. So we can ask the question, are they too difficult to correct? In particular, we found of the HomeKit protocol that is implemented in connected object, and maybe that such object could not be updated. Or does Apple consider the privacy leaks as not serious? Because from the iOS 11.4 to the iOS 13.5, there is likely more than 10 updates, and none of the privacy leaks disclosed here have been addressed finally. So thank you for your attention. Now it will be my pleasure to answer your question.